Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is Module 5, Goodness of Fit Testing. So in this class, and in many of your research projects, you'll be using PDFs that are essentially given to you. They're part of the set of the assumptions that you have when starting your research. But it's important to remember that every time we use a PDF, sort of implicit in that PDF is the understanding that someone before us has conducted the physical experiment or operated the physical system or process that produces the random outputs that are being represented by our random variable. So remember, each random variable represents a physical system or process, and if we're using a PDF that's given to us, we assume that somebody has collected a long data log of many samples of the random outcomes of the system represented by a random variable, generated a histogram, and then found an equation to describe the shape of that histogram. And that's basically where we sort of pick up in this class. However, key to this sort of sequence of events is that the equation that this person has found to describe the shape of the histogram is a quote-unquote good fit for the histogram. And intuitively, we can say, well, yeah, it matches the shape. However, we need to be a little bit more rigorous than that, and in some cases, we need to have a method that can be automated so we can process many data sets. And that's what this module is all about. This module is going to, in a way, kind of deviate from the main theme of the class and talk about a little bit of experimentation, or basically how do you come up with your own PDF equation if you happen to find yourself working with experimental data. And this is a deviation because this is squarely in the domain of statistics. And in general, this is not a statistics class. This is a probability and stochastics class. Statistics deals specifically with the collection and analysis of data, typically random data. And the branch of statistics that we're going to be talking about in this module is goodness of fit testing. And these are methods that determine whether or not a PDF equation that we're using to describe a histogram accurately represents that experimental histogram. Now, there are many goodness of fit techniques. We're going to be talking about, well, I guess maybe two in this module. The first one is the simplest of all goodness of fit techniques, and that's just basically looking at a picture. So on the same plot, you plot the experimental histogram and the PDF, and you just visually look and see if there's a match. Now, this is a very good technique to do first when you're trying a whole bunch of different histogram shapes and you just kind of want to get an idea of what's going on. However, as we're going to see, it does suffer from some problems, but I think this is still a good place to start. Now, if you remember, a PDF is normalized to have unit area, and a histogram is bin size versus sample, or the number of samples that fall into each bin, sample count basically. So we need to somehow scale either the histogram or the PDF so that they match up on the plot. Now, normally the easiest thing to do is just in MATLAB or whatever package you're using, normalize the histogram curve so that it has a unit area. That's usually what I do. However, for the purposes of this discussion, we're going to go a slightly different route because it's going to help lead us into the discussion of the next goodness of fit testing, which is chi-squared goodness of fit testing. So what we're going to basically do, rather than scaling the histogram, we're going to leave the histogram as it is, and we're going to use our PDF equation to predict how many samples should fall into each bin according to our candidate PDF. And then we're going to plot both things on the same plot. And so just to start off, a little bit of terminology. Capital N is the total number of samples used to create the histogram. This is typically in the many thousands or even perhaps millions of data points in some cases. K capital K, is the number of histogram bins. This will vary. I tend to use between 1 and 200 bins when I'm doing my research. HK is the number of samples in bin K of the histogram. So, and this is the experimental histogram. That's what HK represents. Alpha K minus 1 is the lowest value that's grouped into the experimental histogram bin K. Alpha K is the highest value placed into bin K of the experimental histogram. And Fx is our candidate PDF equation. And so the number of samples that our PDF equation predicts should be in the kth bin is just the total number of data samples recorded in the histogram multiplied by the proportion or the probability that a sample falls into bin K. And that can be determined just by integrating our candidate PDF equation over the range of values contained within the bin that we're considering. And we call this the expected number of samples in the bin, and that's why I denote it EK. Okay, let's get started. So in the following slides, we're going to do an example of visual goodness of fit testing, I guess, where I'm trying to see if the exponential equation, a decaying exponential equation, can be used to describe an experimental histogram. And so on the x-axis of this plot, we have the value of our bins, of our histograms bins. On the y-axis, we have the number of samples that fall into each bin. The columns represent HK. That's the number of experimental samples that fall into each histogram bin. And the exponential curve, the smooth exponential curve, those are the values EK, the number of samples that we expect to fall into each bin based on the theoretical PDF equation that we're using. Now, sometimes visual inspection is very clear. And so this is one of those cases. Obviously, this is a terrible fit. HK, the experimental histogram, looks kind of like a uniform distribution. Clearly not a very good match for the exponential equation. So we can clearly discount the exponential equation in this case as being a good fit. And so that's the value in many cases of visual inspection. It allows us to often come to a fairly quick conclusion. This next case is when we're fitting the exponential equation to a different set of experimental data. And here, it seems like the fit really is excellent. So at every sort of midpoint in the bin, we see almost a perfect match, at least as far as we can see visually, a perfect match between the number of samples that we expect and the actual number of samples that fell into our experimental histogram. And so here we can say this is definitely a good fit. Now, that, however, can still sometimes be misleading. We can see, very clearly in these bins with a large number of samples that we have quite a good fit. However, down here in the tail of the distribution, we can't see anything very well at all. And sometimes it's the tail of the distribution that's the most important for us, particularly if we're trying to use the PDF to predict the statistics of very rare events. And so there are a couple of different ways to improve visual inspection. One is to use a log plot. And the other one is to use something called a QQ plot. And a QQ plot is a different way of performing a visual comparison of two distributions. I won't go into any more detail about it in this particular module, but just be aware that if you're trying to do a visual fit and you're not able to see your tails pretty well, a QQ plot will actually show give you excellent resolution on the match that you have in the extreme tails of a distribution. The third example is a little bit more troublesome. So here we have, again, our experimental histogram, our exponential equation, and, it's hard to say, right? I mean, the experimental data kind of seems like it's decaying, but we do have these regions where, we don't have a very good fit. We don't have a very good fit. And even here, this first bin is quite a bit lower than the second bin. So does that perhaps suggest that maybe the distribution might have a steep decline as it approaches the y-axis? And so in this particular case, we're not sure. Visual inspection can't definitively say whether this is a good fit or not. And I would really caution all of you when you're performing your own research, if you're doing sort of PDF fitting, do not let visual inspection be the last word. Even in the previous example where it seemed visually that the fit was excellent, do not let this be the only way that you come up with your PDF equation. We do need a much more rigorous method, and that's what we're going to be talking about next. So there's two problems with visual inspection. One is, it's not really mathematically rigorous. It is still a judgment call. The second problem is it's very difficult to automate. So here I've shown you 3 different data sets, and we were able to go through them relatively quickly. In many cases, in many experiments, you may have hundreds of data sets or thousands of data sets, and it's exhausting and very imprecise to try and do a visual inspection of every single one of those data sets. So we also need a method that can be automated, a mathematical method that can be automated so that a computer can decide for us whether the distribution is a good fit. And that's going to lead us into our next discussion, which is, or the second part of the discussion, which is the chi-squared goodness of fit test. So if we want to automate our goodness of fit test or be a little bit more mathematically rigorous about it, the first thing we need to do is come up with a mathematical metric that quantifies how closely the experimental histogram agrees with our equation. And you could imagine a number of metrics for doing this, and there are a variation of metrics, but the metric that we are going to use for our chi-squared test is shown on this slide. For every single one of the k histogram bins, we take the difference between the experimental number of samples and our expected number of samples. We square that difference to get rid of the sign, and then we normalize by the size of the bin. Okay, so the goal of our goodness of fit test, again, is to compare a data-generated histogram or an experimentally generated histogram to a theoretical distribution and decide whether or not we think it's a good match. And so to understand how the chi-squared goodness of fit test works, let's start by assuming that the distribution is in fact a perfect fit to the data. So that brings the question, well, okay, if we know in advance that our fit is perfect, will our error metric be 0? Will that value of c that we had on the previous slide be 0? And the answer is no. There is still going to be some error due to the fact that we've only got a finite number of data samples. And this is known as sampling error. And just as an example, here is an experimentally generated histogram given by the blue columns, and a theoretical distribution for an exponentially distributed random variable. Now, I actually generated the experimental numbers using an exponentially distributed random number generator. So I know for a fact that the numbers that I generated are a perfect match to the exponential distribution. However, I only generated 1,000 random numbers, and then I divided them into 200 bins. And because we didn't have, there just weren't enough numbers to sort of average together, we don't get, perfect agreement. So some of the bins are a little too high. Obviously, some of the bins are a little low. some of the bins are right on the distribution, but in general, it sort of goes up and down. So even though we have a perfect match, there's still some error. And that's, again, due to the finite number of data samples that we're working with. And that's what we refer to as a sampling error. And so in general, we don't know if our distribution is a perfect fit for our data or not. That's kind of the whole point of doing the test. And so when we don't know if our distribution is a fit, we basically need to decide between two scenarios. Scenario number one is when the value of our error metric C is just due to sampling error, and our theoretical distribution is in fact a match. The second scenario, so I guess maybe this would be scenario number one, or that first scenario would be scenario number one. The second scenario, scenario number two, is when, in addition to sampling error, we also have another sort of source of error in our C metric that is due to a fundamental mismatch between the data and the theoretical distribution that we've assumed. So we've got sampling error plus an additional source of error due to distribution mismatch. And as you might expect kind of intuitively, if you've only got sampling error, your C metric is going to be smaller than when you've got sampling error plus mismatch error. And so, I guess, again, just intuitively, we decide that we've got a match when C is quote unquote small, and we decide that we've actually don't have a match, that our theoretical distribution is wrong, when our value of C is large. And so the whole challenge and the whole purpose of a goodness of fit test is to help us to decide whether or not our C value is small or whether or not our C value is large. So we're going to start by developing a model for the random distribution of sampling error. And specifically, we're going to model sampling error as a chi-squared distributed random variable, which of course is where the chi-squared goodness of fit test gets its name. And first, just some preliminaries about the chi-squared distribution. Let's start by defining a random variable y that consists of a summation of L squared random variables, XL, where each XL represents a zero mean unit variance independent Gaussian random variable. So we're basically taking L zero mean Gaussian random variables, squaring them, and then adding them up. And when we do that, we say that y is a central, because we're adding zero mean Gaussians. Y is a central chi-squared random variable with L degrees of freedom. And so the degrees of freedom term just refers to the number of Gaussian random variables we're adding up. And having L degrees of freedom basically just means that there are L independent parameters that can be chosen before y is completely defined. Or basically we've got L random variables that we can play with, basically. And the CDF for y is given by kind of a nasty integral. It's not a closed form integral, but fortunately we can determine the value of the CDF using the incomplete gamma function in MATLAB. And so you've got the value y, which is your argument for the CDF, and the degrees of freedom L, and you basically plug those into the incomplete gamma function in MATLAB, and you get the CDF value. And so we're going to assume, so kind of fundamental to how we're going to build up to this chi-squared random variable, is that we're going to assume that the sampling error in each individual bin actually has a Gaussian distribution where each hk is a Gaussian random variable that has a mean of ek, which is our expected number of samples in the bin, and a variance of ek as well. And so this is our formula for our mean squared, or sorry, our squared error metric. And so we assume that each of these HK terms are Gaussian random variables. We subtract off the mean, so we're assuming that if we've got sampling error, then our error is distributed around the actual expected number of samples in each one of our bins based on our theoretical distribution. And once we subtract off the mean, then the term inside this bracket is zero mean. We then square it, divide it by EK, which we assume is our variance. And basically what we're doing is we're taking the summation of K squared zero mean Gaussian random variables. So in other words, we're assuming that C has a central chi-squared, or that C is a central chi-squared random variable and corresponds to that distribution. Does the distribution have k degrees of freedom because we're adding up k individual random variables? Theoretically, yes, but in practice, not quite. Now, usually when we are fitting a theoretical distribution to some data, we want the best possible fit. So we want the mean of our theoretical distribution, for example, to exactly match the mean of the data. We want the variance of the theoretical distribution to exactly match the variance of the data, so that as much as possible our distribution, overlays well onto our experimental histogram. And that means that we have to estimate the mean and variance of the data and then plug it into our theoretical distribution equation in order to get the best possible overlay. Now, the problem with doing that is it basically makes our expected values, our EKs, correlated or related to the experimental data, because the EKs are a function of the theoretical distribution equation, and the theoretical distribution equation depends on parameters that we actually extract from the data. So there's a relationship there between, or a correlation between our expected values and our actual sort of experimental values. And that means we don't quite have the degrees of freedom that we used to. Our model doesn't exactly have k completely independent terms. And so to compensate for this, we reduce the degrees of freedom by 1 for every PDF parameter that is estimated from the data. So for example, if we have to estimate mean and variance from the data, the degrees of freedom for our chi-squared random variable C, we would assume would be equal to k minus 2. Minus 1 for the mean and 1 for the variance. This is kind of a hand-wavy explanation a little bit, but hopefully it gives you sort of the intuition behind what's going on. So now that we've got a model for the distribution of the sampling error, assuming that we've got a perfect match, and again, remember the chi-squared distribution assumes that we have a perfect match, we can use it to basically spot calculated values for C that are too big, right? We now have a distribution for the values of C if we've got a perfect match and we've only got sampling error. And now if C is a little bit too big, if it falls outside that distribution of expected C values a little bit too much, then we start to get suspicious, right? We start to think, okay, well, maybe there's more than just sampling error here. Maybe we've actually got a fundamental mismatch between our assumed distribution and our actual data. And that's basically how we spot a large value of C. And so we know that the CDF value, if we give it an argument of C, we know that the CDF function will give us the probability that our random variable y is less than or equal to our argument, right? So if y is a chi-squared random variable, then this is the probability that it's less than or equal to our calculated value C that we got from our actual experimental data. So said another way, Fy, or the CDF argument, when we give it
or the CDF function, when we give it an argument of C, gives us the proportion of chi-squared distributed sampling values that are less than or equal to or smaller than our calculated C, right? That's basically what this probability is. We can also interpret it as the proportion of chi-squared values that would be less than or equal to C. And so basically, if our value of C is way bigger than a very high proportion of typical sampling values, then it's likely that we have a mismatch error as well. Just kind of by convention, we usually don't calculate the CDF value. We usually use 1 minus the CDF value as our chi-squared confidence value, or sometimes it's called the significance value. And the way to interpret 1 minus the CDF of C is it basically gives us the probability that C is due to sampling error alone. So that's typically how we express that. So we want 1 minus the CDF to be as big as possible. And if it starts to get too small, then we start to get suspicious and we start to suspect that we have a mismatch. And so generally speaking, it's a little subjective, but generally speaking, if this confidence value falls too much below 10%, then you should be a little bit suspicious of your match.
There are a few more things that you have to be careful of when you're using the chi-squared goodness of fit test. One thing is that the samples that the experimental outcome samples that you use to create your histogram have to be independent or uncorrelated, which means there can't be any statistical similarity between them. So later on in the class, when we study random waveforms or stochastic processes, we will talk about something called an autocorrelation function. And an autocorrelation function basically tells you how far you have to space your samples for them to be uncorrelated. So that's something to keep in mind when you're doing a goodness of fit test. The second thing you have to be careful of is that there has to be a minimum number of samples in each of the experimental histogram bins. Usually this minimum is between 5 and 10. I've used 5 in my own research with fairly good results. The reason for this is that you need to have a minimum number of samples added up in the bin, or the Gaussian assumption becomes not very accurate because it's based on the central limit theorem. Bins that do not meet this minimum need to be combined with their neighbors. So you basically just take 2 neighboring bins, add them together, and then the midpoint for that new bin would be sort of the average of the center points of the 2 bins that you've combined. And so that means that you've got, once you've done this combining, you have a histogram where not all bins are the same width, right? So if you combine 2 bins together, that makes one really wide bin that might be next to sort of a regularly sized bin. And so you need to keep that in mind. And so let's conclude with an example from my own research. I conduct wireless channel measurements, and one of the measurements I do is to measure a wireless channel and come up with random data samples of the fluctuations that you see in the amplitude of a received wireless signal due to reflections and fading in the wireless channel. So the data that I'm going to present to you consisted of 17,030 independent samples of the fluctuations of a received wireless signal. And I've used that data to create a histogram, and my objective was to see if I could use the Ricean distribution to fit to this experimental histogram. So the Ricean distribution has 2 parameters. The equation for the Ricean distribution has 2 parameters that I had to estimate from the data. And I started with a histogram that had 100 bins. And so the number of degrees of freedom would be 98, 100 minus 2. And that's what I'm showing to you in this slide here. So the red curve is the theoretical Ricean distribution, the number of samples, the expected number of samples predicted by the Ricean PDF equation. And then the blue is the actual experimental histogram. And you can see it looks pretty rough, pretty choppy. Although, visually you can kind of see that, it does seem to track the trend predicted by the theoretical equation. But definitely based on just a visual inspection, we can't say for sure. And so we need to proceed with our goodness of fit test. Another thing that you're going to notice is that we have many of the bins do not meet our minimum, right? So we require at least 5 samples per histogram bin. And so all these bins are below 5, obviously. And so I had a lot of combining to do. So I had to combine these neighboring bins, these neighboring bins, these neighboring bins, and so on. And once that combining was complete, this was the histogram that resulted. So remember that when you combine the experimental bins, you have to combine the expected bins as well, because both values are required to match up when calculating the metric C. And so when you combine the experimental bin, you have to combine the same, the theoretical equation bin in exactly the same way. And so when I did that, and the result, you can see, doesn't bear any visual resemblance to the distribution that we had before. So the red curve is the theoretical expected number of samples, and the blue is the experimental data. You can see visually that we've got a reasonable match, like the distributions do seem to follow each other. You'll also notice that at a few points the expected number of samples falls below the minimum 5. That's okay, as long as the experimental bins are above 5. It doesn't matter if the expected bins are below 5. And so once I was finished combining, we went from 100 bins down to 26 bins. And so our degrees of freedom would now drop to 24 in this particular case.
And if we go ahead and calculate our value for C, in this particular little experiment, I got a C value of 16.76. Our degrees of freedom again were equal to 24. And then 1 minus our chi-squared CDF value when I plugged in 16.76 gave me 0.859. That means that if we had a perfect match to our distribution, then 85.9% of our error metrics would be larger than the 16.76 that we actually got. So that suggests we've got quite a good match. Assuming a perfect fit between the data and our distribution, our actual error value is still smaller than 85.9% of sort of other likely values of C if we had just sampling error. So we can be quite comfortable that we've got a good match here. And again, we would only get suspicious if this value dropped down to around 10% or maybe a little bit lower.